Hello everyone, in today's video we will be talking about applications of symmetry which can be found in chapter 11c, and we'll be talking about integrals. Now we should start off this discussion with the whole idea of, with symmetry and these character tables, what are they good for? Why are we using them? So let's go down the checklist. We can use our character tables in symmetry to assign symmetry symbols for our orbitals. And those are our A1s, our A2s, our B1s, and our B2s that we see. And these should be representative of orbitals inside of a molecule. We can also understand what orbitals can contribute to a molecular bond and whether or not there is overlap which would produce a molecular bond. We want to understand when these overlap integrals are non-zero, because when they're non-zero, that means a bond has formed or a transition has occurred. We can also know when transitions are allowed, let's say a UV visible transition, an absorption event. And we can see something similar to this over in the Jablonski diagram, where we see the absorption of a photon bringing an electron to some excited state into an antibonding orbital. We can either get a fluorescence event or see it migrate through intersystem crossing to a triplet state. So let's get into the details of how we should view these issues. First, we'd like to talk about the vanishing integral. Now, the whole idea of a vanishing integral is most of the time when we are going to integrate over all space, unless we've got perfect symmetry, we are going to see a zero sum integral. So you'll notice here on the left-hand side, if we were to integrate over this space, which all has a positive phase as we integrate, we'll then have a real value, some number that's positive. And then over on the right-hand side, if we integrate over this space, which you could imagine is, here's our orbitals, and we're integrating across these series of orbitals. Once we've integrated, well, the opposite portions of the orbitals are canceling it out, and they're going to be equal to zero. And we'll get into these factoids. Fact: an integral over a region of space can be non-zero only if the integrand or contribution to it spans the totally symmetric, irreducible representation of the point group of the region. And we're going to find out that that really has to be A1. And as we know, A1, depending on which point group it is a series of ones all the way across where we don't have any change. Over here in the bottom right-hand corner, we can kind of get another representation when it comes down to our orbitals. If we were to integrate across this s orbital as an idea, through a symmetry operation, we are going from a plus portion of our orbital to another positive portion. So the symmetry has remained the same. And we'll go through the details of this. First, let's talk about our overlap integral, which is the product of two functions integrated over all space. Here are our functions integrating over x, y, and z, and I is our overlap integral. And most of the time, this overlap integral is going to equal zero. Let's just get right to it. There's only special circumstances in which it is non-zero. We're going to say if I equals 0, and we know the molecular orbital does not exist for function A and function B, or F1 and F2. And of course, these can be orbitals for an S and a px orbital, whatever it happens to be. But a molecular orbital and a bond has not been created. On the other hand, if I is not equal to 0, which is a special circumstance, only if the integrand itself, that integration, has the product F1, F2 is unchanged by any symmetry operation. It has to be unchanged. What does that mean? If you're unchanged by any symmetry operation, well, therefore, it must be the A1 symmetry species. Big fact right there. So now we want to ask ourselves, how do we figure out I? How do we use character tables to do that? We've got a couple steps. Step number one is to identify symmetry species. And remember that symmetry species are just your A1s, your A2s, B1s, etc., of the individual function. From the character table of that point group. And write characters in 2 rows. Seems pretty straightforward. Step number 2 is go ahead and multiply the characters, multiply the numbers. Each column, and write the result in a 3rd row. Seems pretty straightforward. Step number 3, you're supposed to just ask a very direct question. Does the row that you just produced, row number 3, match any other symmetry species? If yes, is it A1? If it's A1, then your answer is non-zero. If it's any other character species, then it is 0, which is quite powerful. All right, let's go ahead and do an example. And we'll use our C2V, our trusty point group. And let's go ahead and we can go ahead and multiply. We'll multiply A2 and B2 of the C2V point group. And by this time, you guys should have a very strong handle. Our sim species. We went through in the other videos what happens after our sim operations. We should always know identity. Going across for A1, it always has to be 1. For A2, 1, -1. These guys are the ones that are rotating, you'll recall, representative of the px and py orbitals. And these ones are opposite, as you'll recall from our previous video. So we're dealing with this set of characters. So now let's go ahead and let's see what happens when we multiply. We'll do A2 and B1. Is it non-zero? What is that integrand? So we'll set it up. We'll do A2, B1. We're going to draw our line for our product, and it's going to give us some product here. So we take our information from A2, which is 1, 1, negative 1, negative 1. We take our information from B sub 1, 1, negative 1, 1, negative 1. And it's as simple as taking these products. So it's 1, negative 1, negative 1, and 1. Interesting. Okay, well, this product, if we check back, are there any sim species that are the same as this? Which ones have 1, negative 1, negative 1, 1? Notice that that's actually the same as B2. So the product A2B1 is equivalent to B2. Well, since the product of A2B1 is not equal to A1, then that answer must be 0. And that is a big conclusion here. Okay. And for other examples, take any symmetry species from any point group and do this product exercise and see what you get. E2H, C3V, it doesn't matter. Just go ahead and multiply these sim species and see if you can achieve A1. Go ahead and pause this video and do D2H or C3V for me. Spend that time and then come back and advance this screen. Well, after doing that work for D2H or C3V, you'll find out that as long as you pick symmetry species which were not the same, you're always going to have some other value than A1. So this is a big fact which we want to absorb deeply. The direct product of two irreducible representations is A1, comma, only if the irreducible representations are identical. In fact check, you can go ahead and go back to that same point group that you just used, and you can keep using all the different sim species you want. But unless you actually use the same species, you're never going to achieve A1. So our product of I, our product of J for that symmetry species will only contain A1 if I is equal to J. Another example, let's see what is the overlap integral of A2 and A2 in the C3V point group. Let's go ahead and make these guys identical. So from A2 and A2, we look in our character table and we notice that it's 1, 1, negative 1. They're identical, so it's 1, 1, negative 1. Create our line. We've got our products. We know that we can see that the product is 1, 1, 1, which is equivalent to A sub 1, totally symmetric symmetry species. The product has A1 symmetry and therefore has a non-zero 0 integrand. This is the type of mathematics which we would then say, well, we must have some type of molecular orbital occurring, or we've got an electric dipole transition. These guys must be non-zero. And so go ahead and practice this on a couple of different groups of your choosing, and then feel comfortable with this process. Thank you very much, and have a good rest of your day.